All right, now the question comes up, how are we actually going to use these ideas? So let's try a practical problem, something that you want to do every day in your life. How many people out there would like to suspend a proton in midair between two electrically charged plates? Great. Oh, I'm glad we thought of it then. All right, so our job now is to find the strength of the electric field in this situation that will support a proton. So we know the electric field, of course, is in newtons per coulomb because it's the force, electric force divided by the charge. So electric fields are newtons per coulomb, just like gravitational field G is in kilograms per newtons per kilogram. All right, now we're going to place the proton, let's say, anywhere. Hey, it doesn't much matter where I put it because the strength of the electric field is going to be the same no matter what. The lines don't thin out. No one goes out radially. They're all parallel with each other. So I can put it anywhere I want inside those plates. So here's our proton, and it's positively charged. So if we look, it's going to actually go, the positives on the bottom are going to push up on it. The negatives are going to pull this way. So the charge has a tendency to drift upward towards the top plate. Well, unfortunately, we do have some forces pulling down on it. We've got mg pulling down. And the electric force, of course, is going to be, force electric is going to end up being pulling upward. All right, and kind of like in line with the electric field. Notice that positive particles travel with the field lines. Negative particles will naturally travel opposite direction of the field lines. So being a proton, it's going to have a tendency to go upward. So what I'd like to do is calculate the strength of the electric field here. So we know a couple things here. We've got the weight of the particle downward and the electric force going up. So if we look here, we know that the electric force is going to be equal to the weight coming down. Those two things have to be equal. All right, we want to suspend it. We don't want an acceleration, so that must be true. Now we've got the force electric, and we have mg. Well, we also know that the electric field strength is equal to the electric force divided by Q1. Who's the little guy in here? Who's the one trapped in the field? Not producing the field, but the one that's trapped in it. Well, isn't Q1 the proton itself? So if we look here, the force electric is going to be equal to Q1 times the strength of the electric field, the thing that we're looking for. So we can make a substitution over here. Q1 times the strength of the electric field is equal to mg. All right, and we're looking to find the electric field strength like that. So we'll end up with the electric field is going to be equal to the weight of the proton divided by Q1, which is the strength of the proton. So we know the mass of the proton, common knowledge, is 1.67 times 10 to the negative 27th kilograms. We know the charge on a proton is the same as the charge on an electron, 1.6 times 10 to the minus 19th coulombs. Let's assume we're doing this on the planet Earth, so we could use a G value of 9.8 strength, meters per second squared, or we could do it in newtons per kilogram. Either way would be fine. And we can now solve for the strength of the electric field.